Okay. Let's get the going from current slide. Okay. Now, just a couple of notes. I've said this several times, but I just want to make sure everybody understands it. Because Chris had a doctor's appointment on Tuesday, we decided not to have class without him and to have class tomorrow instead. Thank you, Chris, for bringing us in on a Friday. So it's all his fault now, right? Okay. No, I had a doctor's appointment on Tuesday, so I couldn't be here. So the class decided, with no coercion whatsoever, to have class tomorrow morning from 9 till 10:15. That's what y'all decided, right? You battled it out and came up with 9 to 10:15. So I will try to be here at 9. If things go well, I'll be here at 8. But if they insist that I come by the Birmingham campus, I've got to go by there first and then come here. That might be running a little late, but hopefully that's not going to happen. And then after class, I hope I'll continue working on this campus. But if they insist I go back to Birmingham, I'll have to do that. So I can't tell you where I'll be before or after, but I'll be here at 9. We'll go till 10:15, and we'll get the class done. If you can't be here, it'll be on YouTube, okay? But try to be here if you can. All right. Now, other things, because of my doctor's appointment on Tuesday, I had to end my 112 class that I had this morning 45 minutes early, okay? So what we did with that class, we started 15 minutes early on Tuesday. We started 15 minutes early today. We'll start 15 minutes early on next Tuesday as well, and that makes up my 45 minutes there. We couldn't do that in this one because I had a class before and y'all had classes afterwards. But anyway, we're going to get it done tomorrow. So if you're looking for me before 8:30 on Tuesday, I will be in that room before 8:15 actually, and but then after that I'll go back to normal schedule. Now the other thing that's changed from what it was at first of the term is that now those are all temporary changes. Once next Tuesday's over, all that's taken care of. Okay, but one permanent change for the rest of this term. The first mini term, I had a physical science class that started at 1:15 on Tuesday and Thursday. So my office hours were when this gets over with at 11:15 till 1:15. But starting last Tuesday, this second mini term, the physical science class, the second physical science class doesn't start until 3:15 because some of the automotive students are taking it and they don't get out of their block schedule until 3 o'clock. So therefore, I couldn't start that class until 3:15. Which means, good news for you, and a little bit for me too, I have longer office hours, 11:15 to 3:15, Tuesdays and Thursdays, okay? The bad news for me, I'm here till 7:45 at night, okay? So, because that's a mini-term class, 2.5-hour class, 2-hour lab every day. Tonight we may get through a little early just because the lab, but it's a long lab and the odds of them finishing early is not very good. All right, any questions on anything we've done so far? And here's the other thing that I announced before, so let me say it again now, because I did see an email that confirmed it, that the midterm progress reports are due by tomorrow, okay? Which means if you have a D or an F at midterm, I have to report that, and then hopefully someone will get in touch with you, see if there's any way we can help, get you tutoring, or whatever the problem is, okay? Now, some of you, I don't think need any tutoring or help or anything else. It's just, I don't have any scores for you. I have 1 paper and 2 first tests turned in, and that's all, folks. So everybody else has the first test out. Everybody has the second test out. If I have no score for you, that's the F at midterm. Not that it counts anything, but it might just cause you just a tad of having to deal with somebody seeing if you need tutoring help. So if you could get me something today, or if I'm here tomorrow, I'll be here tomorrow, get me something by tomorrow. That way I can do the midterm progress report and not have to report on you. Okay, so please I've only got 3 things so far out of, what is it, 7 students, 8 students, 9 students, okay? Only a third of you have turned something in. And I think I really encourage you, try to get that first test in before I gave you the second test. Only 2 of you have done so. Please don't get behind. It's that much harder to catch up. All right, any questions? All right. I know who's been here. Dr. Bryant always does his little 4 marks check to see if the markers are worked well. Okay. All right. Here's where we left off last time. We had started talking about the fundamental trigonometric identities, because Chapter 5 is analytic trigonometry. Okay? 5.1 is using the fundamental identities. Here they are. Okay? Now, we just did the basic Pythagorean identity, right? Sine squared plus cosine squared equal 1. That is one to always remember. It's all these are always true. That's one you'll use a lot. Okay? Now, did I talk about how you get the other 2? Okay, dividing this by cosine squared gives you this one. Dividing this by sine squared gives you that one. Okay. Now, each of these can be expressed in other ways, too. And let me show you what I mean by that. Okay? Let me get my pen set up. All right, let's take this one. Okay? Here's another way you could express that. I'll write down the original. Sine squared, they're using u, plus cosine squared u is equal to 1. Know that. Remember that. Let's subtract cosine squared from both sides. Last we divided by cosine squared. Let's subtract cosine squared from both sides. Okay? And that then gives us sine squared u is equal to 1 minus cosine squared u. Okay, there's another. That's a real simple, right? But you could also take the square root of both sides, have sine u is equal to either plus or minus the square root of 1 minus cosine squared u. Okay, there's another one, and you'll see that fairly frequently. Okay? Or you could have subtracted a sine square from both sides and had the same thing in terms of cosine, that cosine squared u is equal to 1 minus sine squared u, right? Or you could take a square root of that and have cosine u equal plus or minus the square root of 1 minus sine squared u. Okay? So there's, 4 more identities just based on this one. And these 2 are based on that one. Or, look at this one. Let's subtract a 1 from both sides. And that would give us a tangent squared u is equal to secant squared u minus 1. That's another trig identity. It's a Pythagorean identity. It's this one just rearranged. Or you could subtract its tangent squared from both sides and had secant squared u minus tangent squared u is equal to 1. There's another one, okay? There's tons of different ways you could do that. Or, yeah, I already did that. Oh, or you could take the square root of this one and have tangent u is equal to plus or minus the square root of secant squared u minus 1. There's another one, okay? All right? And then we can do the same thing with the other one, okay? Subtract, move around square roots. How many different forms can you write the Pythagorean identities? And you use them all at some time or another. So get familiar with them, get used to manipulating them. Feel free to do it. Make sure every step is right. As long as every step is right, then probably your new identity would be right too. Okay. Now, I'm trying to remember, we did talk about, yeah, I'm pretty sure we did, about your cofunctions, right? We did. Let's start with any old right triangle. Just assume that's a right triangle. Okay? Let's just let this angle here be U. Okay? Can you tell me what this angle up here is? Remember, that's a right triangle. That's a right angle down there. A little up. Yes, 90 minus U or pi halves minus U. Depends on which you prefer. Radians or... So that angle up there is the complementary angle to U, right? They differ only by 90 degrees or pi halves, okay? One step, okay? Now, let's name these three sides, okay? What you want to name the sides? Are you okay with X, Y, and R? You're okay with those? Okay. Now, what is the sign of U in terms of X, Y, and R? Y over R, perfect. Okay? Now, tell me what the cosine of pi halves minus U is. This angle up here. It's also Y over R, isn't it? Okay. And here's Jake. I think it is. All right. Okay. So what did we just discover? There it is, right there. So we need these co-function identities. And if we had done cosine first of U, that would be X over R, and sine of pi halves minus U would be X over R. So the sine of pi halves minus U is the same as cosine of U. So the sine of the complement of an angle is the cosine of the angle. That's where the code comes from. And the cosine of complementary angle undoes the code and makes it the sine. And the same is true for tangent and cotangent and secant and cosecant. That's what the codes are there for, of the complementary angles. Okay? Does that make sense? And you knew that without really realizing you knew it. Okay? You can use that one triangle and do all of those with it, right? So the tangent of U would be Y over X, and the cotangent of pi halves minus U would be Y over X, okay? Adjacent over opposite. Exactly. So all of those work. Okay? Now, not sure we did the even or odd identities either, did we?
Yeah, we only got to the Pythagorean.
Yeah. So let's see. We have graphed these, haven't we? That was the section 4.5, I believe, and 6. Okay? So let's harken back to our graphs. Is it all right for me to erase some of the scratch I have here? There's so much writing on this. I really need more room. Okay? So let me erase that. And where can I find room to write? Let's try it here. Let's do, let that be our y-axis, and that be our x-axis. Okay? Now, let's come over here, pi halves, pi, 3 halves pi, and 2 pi. Okay, and do the same thing in this direction. Okay, and we'll go up or down 1. Okay, I think we're okay there. You tell me how the sine function looks. What are some points on it?
It starts at 0.
0, 0.
And then it's going to go to its max to the right.
Okay. Okay, and that will go to 1. So sine of pi halves is 1. Sine of minus pi halves is negative 1. Sine of pi is 0. Sine of negative pi is 0. Sine of 3 halves pi is negative 1. Sine of minus 3 halves pi is positive 1. Sine of 2 pi is 0 and 0. Okay. That's kind of how the sine function looks. I don't draw well, but you get the general idea, right? Now, what can we notice from this? If you go a little bit to the left here, you're having to go down. A little bit to the right, you have to go up, but that's the same amount, isn't it? So what do we call that? When the function does opposite things on either side of the zero. Say again? Yeah, good choice. Okay, it's an odd function because sine of negative u, if you do your u this way, you're going down, but if you go the other way, you're going in the opposite direction, so that's minus sine of u. That means it's an odd function. Now, what's the reciprocal of sine? Cosecant. And if sine is odd, cosecant has to be odd. Okay, so that's an odd function. Now, let's harken back to what tangent looks like. You want to do that in a different color? Which? Red. Okay. All right. What can you tell me about tangent before I do anything about drawing it? Okay. Define for me what tangent is, as in right there. Sine over cosine. Okay. So perhaps I should have done cosine first. Let me go do cosine first. Give me a different color for cosine. Second? Blue? Is that what you said? Yeah. Okay. Light or dark? Dark. Okay. So here, you said green, didn't you? No, okay, all right. I can't hear, so I'll just make something up. Okay, where does cosine begin? 1, and goes down to 0, and goes down to negative 1, and goes up to, and back up to, and on the other side, negative pi halves, it goes at 0 first, then the negative 1, up to 0, and up to positive 1. So this is how cosine looks, right? Something like that. All right? Now, what kind of function is cosine? Mine's graph is what? Even function, because whatever it does over here, it does the same thing over there. So cosine is, cosine of minus u is cosine of u. And what's this reciprocal? Oh, what do you wait? Goodness gracious. Okay. Gavin's here. All right, he's still my heart. Never mind. Okay. So right now we're only missing Josh and Jalen. The 2 J's are missing. Okay. So cosine is even. What's its reciprocal function? Secant. So that must be even to, sure enough, it is. Now let's go to tangent. And we said tangent was It's going to be red, by the way, because that's what y'all asked for, unless you said green. Okay, all right. Okay, I don't know why it does that, but it did it. Okay, tangent is sine over cosine. So what do we know right off the top? What do we have to watch out for?
U to be for 0.
No, we're cosine u. Okay, and cosine was our blue function here. So everywhere that cotangent is 0, tangent is undefined, because you can never divide by 0, right? Well, you can pick those out right here. There, cosine was 0. So there's a vertical asymptote. There's cosine 0, vertical asymptote. There, cosine is 0, vertical asymptote. And there, cosine is 0, vertical asymptote. In other words, at every half pi, you have a vertical asymptote. Okay? Now, where is tangent halfway in between those vertical asymptotes? Any idea? 0. 0, 0, 0, and 0. And why do you reckon that's true? Because anywhere sine is 0, that's going to make tangent 0, right? You have 0 over something. Okay? So sine is 0 there, and there, and there, and there, and there. All right? Now, where does tangent go in the first quadrant? Everything is positive in the first quadrant, so it's going up. And it obviously can't ever touch that line there. It's going to infinity there. Now, at pi quarters, you want to know what that is? Tangent is pi quarters is sine over cosine. And if they're the same values, 1, all right. It's 1, okay? So the tangent is 1 at here. But how about in the fourth quadrant? What is tangent? Negative. And that'll be a negative 1. So here it's a negative 1. Here it's a positive 1. Here it's a negative 1. And so on and so forth. Okay? Here it's a positive 1. Here it's a negative 1. Here it's a positive 1. Okay? So tangent must be going something like this. Something like this. Something like that. Something like that. Something like that. Okay? Something like that. That's tangent. Okay? So what do you think it is as far as even or odd? Tangent of negative u is the opposite of tangent of u. So that's an odd function. So sure enough, tangent, and therefore its reciprocal is cotangent. It will be odd also. Okay. So 4 out of the 6 are odd functions. Only 2, cosine and secant, are even functions. Okay? So there's 6 more identities that you know. Sine of negative u is negative sine u because it's an odd function. So is cosecant, so is tangent, and so is cotangent. The cosine and secant of negative u would be cosine u and secant u because those are even functions. Make sense? So there's our table. The ones we use the most are the top 3. Reciprocal identities, quotient, or I call them ratio identities, and the various Pythagorean identities. And there's tons of ways to express those. They all come from this one, by the way. Every one of them. All right. Can I erase the scratch? Well, I don't need to. Let's just go to the next thing. Here's what I was saying. Pythagorean identities are sometimes used in radical form, and there's a variety of ways. There's sine u is plus or minus the square root of 1 minus cosine squared u, or cosine u is plus or minus the square root of 1 minus sine squared u. Tangent u is plus or minus the square root of secant squared u minus 1, or secant squared u is plus or minus the square root of 1 minus tangent squared u. So you can write them anywhere. Now, this is a little bit bothering here. Why are the plus or minuses here? I know we took square roots and you have to put them. What does that mean for us?
You get two numbers from the radical, either positive or negative.
Okay, from any radical? Not quite. It's close. You're right on the money. What you deal with, though, if u is in the name of quadrant. Name of quadrant. Second quadrant. Cosine u is the second quadrant. Negative in the second quadrant. The sign is positive. So if u is in the second quadrant, you use the plus sign here because sign is positive in the second quadrant. If secant is, well, that's the same as cosine. It would be negative in the second quadrant. The tangent would be also negative in the second quadrant. So it depends on where the u is, or u r, or whatever. That determines which sign. So it's not either sign. It is either sign, but you only have one at a time, depending on where you are. Where are you, Waldo? Figure that out, and you got your signs right. Okay? So let's use the fundamental identity. Oh, I thought we just needed to know them. Okay, we're going to actually use them. Okay, one common application of trigonometric identities is to use given values of trigonometric functions to evaluate other trigonometric functions. All right, so here's one. Use this one value. That's all you get. No, you get two pieces of information. Secant u, let me go back to dark, black. Okay, secant u is equal to negative 3/2. Time out. Is that even reasonable? Can secant u ever be negative 3/2? If that were sine u, could that be true? No, because sine is always between plus or minus 1. How about secant?
Can it be outside?
Yes, it's always outside plus or minus 1. So that sure enough is. It's less than minus 1, so that is a legitimate value right there. Okay? So we feel good about that. Okay? So secant u is minus 3/2. And secant can be negative? Can it? That's the question.
No, because it's even.
Okay. But what if the other side is negative?
Yeah.
Yeah, of course it can. Okay. Now, where is secant negative? Anybody? Where is secant negative?
Second quadrant.
Second quadrant or third. Second and third. Because guess what? Secant is 1 over cosine. Cosine is x over r, right? And x is negative everywhere to the left of the y-axis. So cosine is negative here and here, and secant is negative here and here. Cosine is positive here and there. All students say calculus. Okay, so the cosine is positive there. All right, so we know now that u has to be either in the second quadrant or the third quadrant. Okay? And we know its secant value is negative 3/2. Okay? They give you one more piece of information. Tangent u is greater than 0. Where is that true? It's another way of saying tangent u is positive, right? Where is that true? It would have to be what? Third, exactly, because tangent is positive in the first, the secant isn't negative there, okay? But tangent is positive in the third, and secant is negative in the third. So we know not only its value, but where it is. Where are you, Waldo? Okay. So we know that. So let's find the values of all 6 trigonometric functions. Now, my suggestion here is to draw a circle. That's not what they want to do. but that's my suggestion. So we want to do all 6 trigonometric functions. We want to know what sine u is. We want to know what cosine u is. We want to know what tangent u is. We want to know what cotangent u is, or u are, I don't know. We want to know what secant u is. And we want to know, well, we know what secant u is. It's minus 3/2. They told us that, right? And we want to know what cosecant u is. Which of those 6 is the easiest to find? Why? It's the reciprocal. So what would it be? Negative 2/3. Is that a legitimate value for cosine? Sure it is. Okay. Now, they want you to use those other identities. But you know what? I find it so much easier, and you really are using the identities in some sense, a stretch of a sense, but I suggest that we draw a circle, okay? And I should have drawn the circle before I put the axes in, because sometimes my circle doesn't fit too well. And what radius do you think I want this circle to be? Hint, look at cosine. Okay, you might be able to do it there. I don't want 1 though. What is cosine? Okay, and what is cosine defined as? 3. I want that circle to be 3. Radius 3. Okay, and right now we know that the x value is minus 2, but we already determined don't go up, go down. So here's the angle right there. Now, my circle isn't a very good one. There's the angle u right there. It's in the 3rd quadrant, and the x value is negative 2, and the r value is 3. Okay? Now, with that in mind, so x is minus 2, r is 3. Can anyone tell me what the y value is? And what would that give you? Anybody? What would that give you? Square root of 5. Plus or minus? Minus, because you're in the 3rd quadrant. Minus root 5. And guess what? You can write down every one of the rest of these, can't you? What is sine?
Where's the angle at?
Second?
Where's the angle?
The angle is this u here, this thing right here. Want me to put it in a different color?
So where would it be on the triangle?
Okay. All right. The reference angle would be right there.
So sine would be negative square root of 5 over 3.
Perfect. How about cosecant? Negative 3 over root 5. And if you don't like root 5 or radical in the denominator, that could be written as
3 square root of 5 over 5.
perfect. What would be your tangent function? Is what? Not over 5. Tangent is sine over cosine. So just pretend you're going to divide that. The 3's go out, and that gives you square root of 5 over 2. Plus or minus? Plus, because minus divided by minus is plus. And you're in the third quadrant, tangent is positive in the third quadrant. All these things fit. What would the cotangent be? Yeah. Say again? 2 over square root of 5, and if you didn't like radical 5 in the denominator, you could write it as perfect. Okay. There you go. And in reality, we only use, well, we use one trigonometry to get here, or to get here, and then we used our circle. I used the 3 circle here because the radius was 3, and we knew the cosine would be negative, the u had to be, the x value had to be negative. From the fact that tangent was positive, that meant you had to be a third quadrant, so that meant that y value was negative. And Pythagorean identity, Pythagorean theorem told us it was negative root 5, and then after that we were able to determine the sign using a reciprocal function. Reciprocal identity, we were able to get cosecant. Using the ratio identity, or the quotient identity, we were able to get tangent, and then the reciprocal identity, you were able to get cotangent. So yeah, we use those identities everywhere. The book wanted you, once you had this, to use the Pythagorean identity to get sine. I found it so much easier to use the circle to get sine. But then after that, you're using your identities, right? Make sense? All right, good deal. Let's see how the book did it. All right. Using the reciprocal identity, that's the easiest one right off the top. Jalen's here. Okay, so we're only missing Josh. Okay. He's almost always here, but not here today. He's the only one on this side of the room with me. Okay. Now, so we know since the cosine is the reciprocal of secant, we knew secant, that's going to be 1 over negative 3/2, or just negative 2/3. And that makes sense. Now, what they do next is use the Pythagorean identity, which really we use Pythagorean theorem. Same deal, but to me the theorem's easier than identity in this case, because see what you have to do is sine squared is equal to 1 minus, and we know what cosine squared is, it's negative 2/3, so it's 1 minus a negative 2/3 squared. Well, negative 2/3 squared is a positive 4/9, right? So 1 minus a positive 4/9, let's write that 1 as 9/9 minus 4/9. That would be 5/9. So then you take the square root of that, and you get, because secant is negative and tangent positive, it follows that u lies in quadrant 3, which we've already determined. So then the sign would be negative. So we take negative square root of 5 over 3. That's their rationale. And it's fine, it's perfectly good, but you could also do it with the circle. And I find the circle a little easier. But you may not. You may like this better. Fine, go for it. Okay? Knowing the values of sine and cosine enables you to find the values of all 6 trigonometric functions. Okay? To me, the next easiest one is cosecant, and that's what they do. It's the reciprocal of that, which is, anyone see their error? Where'd that 2 come from? That's secant. That's not cosecant. That should be a root 5. Okay? Duh. Okay. Josh is coming in. Okay. So, to rationalize the denominator, it becomes negative 3 root 5 over 5. Okay. Now, since you know sine and cosine, now, can you believe this? They're calculating what secant u is. If you recall, the problem gave you secant u. You don't have to calculate it, okay? And what's more, they're doing cosecant. I can't believe that. Okay. This line right here should have been here, and this should have been up there. Okay. Their typesetter on their slideshow was going to sleep on this one, where he doesn't know trigonometry 1. Tangent is merely the ratio of sine to cosine, as they say here. So it's minus this to this. Your 3's can go out, and that minus over minus is plus root 5 over 2. Okay? Pretty easy to do. Ratio or quotient identity. And then the cotangent, reciprocal of that, 2 over root 5, which is 2 root 5 over 5. Okay. So let me correct this. All right. These two things they got backwards. Don't know how, but they did. Okay. Any questions on that? All right. So, given one trig identity and one other piece of information to help you figure out what quadrant you're in, you can get all 6 of them. No problem. Okay? Let's move on to example 2. Oh, and by the way, every example is followed by a checkpoint. Please try to do the checkpoints. Okay? Soon after class as possible. So here we have simplify this expression. What could you do to simplify that expression? What's one thing that might come to mind? Anything? Yeah, factor out a sine. Okay, that could simplify it. Sine x, and what are you left with? Cosine squared x. Second?
I said the wrong thing. Yeah.
Okay. Help me out then. What's left? You factor out the sine? 1. Perfect. Okay, is that as simple as you can get it? Okay, here's a hint, folks. Anyone got an idea? Here's a hint. Anytime you see a squared, think, can I get a Pythagorean identity out of that? Because if you think back on it, every one of those had a square in them. Okay? So does that look at all like any Pythagorean identity? How so? Okay. 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 Now that is one thing you do. If you're factoring, you can certainly do that. Sine x times what you're saying is cosine x plus 1 times cosine x minus 1. Is that what you meant? Is that what you were saying, breaking them up like that? Factoring? Okay. So that is one thing. Frankly, when I look at that, it doesn't really look that much simpler. It is factored, which usually we like factoring. If this was equal to 0, that would be exactly what we'd want to do with it. But what they're saying is simplify the whole expression. And what my suggestion was is that cosine x minus 1, cosine squared x minus 1, look at all like any one of the Pythagorean.
Would that be equal to sine?
Close. Negative sine squared. You're absolutely right. Because we know that sine squared x plus cosine squared x, there's that cosine squared, is equal to 1. There's your 1. Okay? But what they did, they subtracted 1 from both sides, and they then also had to subtract a sine squared x from both sides. Okay? These went out, and that left you cosine squared x minus 1 is equal to minus sine squared x. So if you took that, get out of there, okay? If you took that and made this sine x times a negative sine squared x, that gives you what? Get out of there. Cubed x. Now that looks simpler. Now you're right, in a sense, if you're solving an equation, this would be how you would simplify it into factor form, and that would be fantastic to use. If you're just trying to get it to look as simple as possible, that's about all we can do. Okay? I think that's probably what the book chooses to do too. Let's take a look and see. Does anyone need this a little? Yes?
Can you explain the top right? If you put sine squared x, I don't know if that's plus or minus.
That's a plus. You don't know if that's a plus or minus. Okay? Pythagorean identity. Sine squared x plus cosine squared x is equal to 1.
I was just wondering how you got equal to 1. Is that just part of
Yeah.
Okay.
This is the one. By all means, folks, remember that one. That is just about the most important. Sine squared x plus cosine squared x is always, always, always equal to 1. No matter what value x is there, nothing is. What symbol you put there is always 1. Okay. And then we were trying to get something that looked like this, so we needed to subtract 1 from both sides. So that still had this in it, so we subtracted the sine squared from both sides. We came up with that. Okay? Then, when we plug that in for here, now we got a simpler looking thing. Now, I agree with you, this is not very useful for solving an equation. So this is just simplifying the expression. That would be how you would do it if you were solving an equation. You would certainly want to go that route. Okay? But they were just saying, simplify this expression. That's as simple as you can get, I think. Anyone need it a little longer? Let's see how the book did it. Okay? Well, first factor out the common monomial factor. And, I'm sorry? Go back what? Well, actually, I erased it, so I can't. Yeah. What's that? Okay, how so? Oh, no. There isn't but one side of this. We're just simplifying. It's not equal to anything. That's why I said it. If this was an equation, yeah, we'd go it differently. This is just an expression. We're just trying to simplify it. Okay? So, first thing they said, factor out the common factor exactly like y'all saw. And when you factored it out the sine squared, that left you cosine squared minus 1. Okay. Now, when you're simplifying these things, when you see the squared there, think, is there any way to get a Pythagorean identity out of it? Use a Pythagorean identity to simplify, and that's where we went with this. And here's what they did. They first factored out a minus 1. When they factored out a minus 1, that reversed these two. So they did it slightly different. If you see that better, if that makes more sense to you, do it that way. They factored out a minus 1 out of this, put the minus 1 out front. So that made this a minus and that a plus. Okay? So now they look at that and say, that's exactly a Pythagorean identity. That is sine squared. So it's minus sine x times sine squared x, which comes out the same thing that we got, minus sine cubed x. Okay? We're only dealing with that one expression. There was no equation there, so there's only one side of an equal sign there. This side or that side, but you only got one thing you're dealing with. Okay? Now, that was example 2. They're skipping example. Oh, and by the way, there is a checkpoint at the bottom of the page. Please do the checkpoint. Now, they're skipping example 3 for 5, and 6 before they get to example 7. So let's just do example 3. Factor each expression. So this time they're telling you factor it. The first of these is secant squared theta minus 1. Okay? Is that factorable? What you think? Anybody? Secant theta times secant theta. You're absolutely right. That's how you could factor secant squared theta. Plus 1 and minus 1. Perfect. That's it. That's done. Okay? And I think you'll see that's exactly how they did. Pretty simple, straightforward. Okay? How about the B part? The B part says factor this. 4 tangent squared theta plus tangent theta minus 3. Is that factorable? Second? Okay. No! Okay. Well, is 4 tangent squared theta factorable? Okay, let's do a 4 tangent theta, and the other one would have to be a tangent theta. Okay, now that's clever to do. The reason I wouldn't do 2 and 2 is that you'll not wind up with a plus 1 in the middle. Okay, how you solve that without doing it, I'm not sure, but good choice. Okay, now where do you look next? Now again, we're doing trial and error. This may not be right, but let's try. Okay? Where do you look next? Sign of the last term is, which tell you these two signs have to be? One positive, one negative. But I may have that wrong. Okay? Now what are some possible factorizations of 3? There is 1. 1 and 3. You want to do it that way? 1 and 3. Okay. Now this isn't going to work, I'll tell you. But let's try it and see. Okay? Certainly 4 tangent theta times tangent theta is 4 tangent squared theta. That part works. But this gives you a minus 12 tangent theta plus tangent theta, that would be minus 11. Way off. Wrong number. So let's change our numbers and put the 3 on one side and the 1 on the other side. So let's make that the 3 and that the 1. Okay? Now let's see what we've got. We still got 4 tangent squared theta here. Now we've got minus 4 tangent theta plus 3 tangent theta. What does that give? Minus tangent theta. Again, but this time you're only wrong by a sign. So if your sign's wrong, change your sign. Okay, if the number's wrong, change your numbers. If the sign's wrong, change your sign. So let's change that plus to a minus and change the minus to a plus. Okay? Now let's try it. 4 tangent theta times tangent theta is 4 tangent squared theta. Plus 4 tangent squared, plus 4 tangent theta, minus 3 tangent theta. That gives us a plus tangent theta, and then a minus 3. That's right. We got it. Okay? Clever thought to do 4 and 1 rather than 2 and 2. But I could tell 2 and 2 wasn't going to work. But yeah, that one works. So sometimes, you see, you're just treating tangent theta as if that was an X or a Y. You know, just treat it as a single unit, and it works. Okay? Any question on that? All right. That was example 3. And there's a checkpoint following that. So please do your checkpoint. Okay? Example 4. Let's see if we can do this right below this one. Let's factor cosecant squared x minus cotangent x minus 3. Wait a minute, folks. That would be like x squared minus y minus 3. You can't factor that, can you? So there's no way to factor it? It sort of looks that way, doesn't it?
You can factor out the first two.
Why can you factor out the first two?
If you change what is cotangent to what cosine and sine.
Ah, now there we've got something. In fact, what I suggest is change everything to sines and cosines and see if anything will come out. Okay? Or, wait, there is another possibility. Remember what I also said about anytime you see a square, think Pythagorean identity. Is there a Pythagorean identity dealing with cosecant square? 1 plus cotangent squared, there's your cotangent. I think that will work without doing sines and cosines. Let's change this to 1 plus cotangent squared. Is that what you said? Okay. I won't need the parentheses even, will I? Okay, so let's not do that. That's what cosecant squared is. Okay. Minus cotangent x minus 3. Okay. What would you do next? All right, yeah, combine like terms. That gives you cotangent squared x minus cotangent x minus 2. Now that looks factorable. Don't know if it is, but at least it's got all the same values. So what's the only way that cotangent squared will factor? Cotangent x times cotangent x. All right, that's doable. Now, we look where? Sign of the last term is negative. What did it tell you about these two? One positive, one's negative. And what's the only possible factorization for 2? 1 and 2. Let's see if that works. Cotangent times cotangent, sure enough, is cotangent squared. Cotangent times minus 2 is minus 2 cotangent x plus cotangent x, that would be minus 2 plus 1. Negative cotangent x minus 2, yes. Got it on. So, again, when you see those squares in there, at least investigate the possibility of a Pythagorean identity to help simplify things. That worked really well here. It would have worked doing sines and cosines, but you had a little bit more work to do. I think we're probably better off this way. You get the same answer, by the way. You want to see it done that way, or you want to leave it alone? It's up to you. All right. Let's see, we got the same answer they did. Good for them. All right, there is a checkpoint there too. Please give that a shot. Now, example 5. This is one that you can find in larsonprecalculus.com, an interactive version for this type of an example. It may not be exactly the same, but it'll be somewhat similar. I think I'm going to erase here because this could take a little more room. All right, to erase? Okay. Here's what we got. Sine t plus cotangent t times cosine t. Okay? That's what we're supposed to simplify. Okay? Now, what's wrong with that picture, folks? Three different trig functions in one expression. Oh boy, not so good. But, on the other hand, and none of them are squared, so you can't pull in a Pythagorean identity to help. So in a problem like this, what I like to do is get everything in terms of sines and cosines, see if anything falls out. Well, sine is already in terms of sine, that's just sine, right? How about cotangent? What is that in terms of sines and cosines? That's cosine t over sine t, right? And that's multiplied by cosine t, which is already in terms of sines and cosine. Okay? Well, that becomes sine t plus cosine squared t over sine t. Now, usually when you have a fractional form, let's get everything over a common denominator. What's your common denominator there? Sine. Okay, well, you already got the cosine squared over sine. If you wanted this over sine, what do you have to multiply its denominator by? Sine, so let's do a sine down here. But if you multiply the denominator by sine, what did you better do? Numerator by sine 2, that'll give you a sine squared, won't it? Okay, now let's see what we got. Let's put everything over that common denominator. That would be a sine squared t plus cosine squared t all over sine t. Now you tell me, Jake, what's sine squared t plus cosine squared t? 1. Excellent. Okay, so that is 1 over sine t. And what's 1 over sine t? Cosecant t. So we started with something in sine, cotangent, and cosine, and wound up with something in cosecant. But that's a lot simpler. Okay? Aren't these fun? Say yes. Okay, good. All right. They are. They really are. Sort of challenging, but a lot of fun. There is a checkpoint there. Please go for that. Okay, now we just were sort of doing this. Let's do it again. And let me go on and simplify, erase. Can I erase this? Everybody got it? Okay. Okay. See if we can get this one done. Perform the addition and simplify. So here's our, okay. For some reason when I move the screen, it must do something somewhere and make that go out for a second or so. What we have here is sine theta, okay, over 1 plus cosine theta plus cosine theta over sine theta. Okay? Now we're adding two rational expressions. Okay? How is the only way we can add to fractional forms? What do you need? Common denominator. What's common between 1 plus cosine and sine? Absolutely nothing. So what would be the common denominator? The product of the two. Multiply the two together. So we're going to have to multiply this by what? Sine theta. If you multiply the denominator by sine theta, what did you better do? Numerator by sine theta as well. That makes it sine squared theta, right? And in the second one here, what do we better multiply by? Get the same denominator. 1 plus cosine theta. Okay? But if you multiply the denominator by that, you better multiply the numerator as well. 1 plus cosine theta. All right. Now let's do what we were told to do. The first numerator is just sine squared theta plus cosine theta plus cosine squared theta, right? All divided by 1 plus cosine theta. Don't multiply all that together. Leave that factored. Times sine theta. That's your common denominator, right? So when you have two fractional forms, same denominators, add the numerator to keep the denominator. So that's what we did here. Now, what does that suggest you might be able to do next? Anything? I think Jake's going to help us, right?
I honestly didn't hear you.
What's that?
I didn't hear what you asked.
Okay. What would be something you could do here?
Cancel out like terms.
Okay. How do you mean that?
Like the cosine on the bottom and cosine on top, do they cancel out?
Oh, no. Okay. You can only divide out things that are multiplied. This is added. This is added. They're not multiplied by anything. They're not yet.
You know, the sine squared with a g, and cosine squared g is equal to 1.
Ah! There we go. That's why I thought Jake was going to pick up on that. Okay. Yeah, that's what he meant. Okay. These two add to 1. Okay. All right. So this becomes 1 plus cosine theta over 1 plus cosine theta times sine theta. And now what do you notice you can do, Dawson? Yes, now we can divide out things that are multiplied. And what does that leave us with in the numerator? Help me, help me. Yeah, 1. So you're left with 1 over sine theta. And what's that? Cosecant again. They like cosecant, don't they? Okay, cosecant theta. There we have it. All right, there is a checkpoint. Please follow up with the checkpoint. All right, now I think we're out of time, aren't we? Sadly enough. Who would have thunk it, okay? So we're going to pick up next with example 7. And let me give you some homework exercises, because I know you would be very upset with me if I had a weekend with absolutely no homework to do. So let's get some homework exercises. Do any of the odds 7 through 11. They're all at Calc Chat. 7's at Calc View. Do any of the odds 13 through 17. They're all at Calc Chat. Do either 19 or 21. They're both at Calc Chat. 19's at Calc View. Do any of the odds 23 through 31. They're all at Calc Chat. 25's at Calc View. Do any of the odds 33 to 39. They're all at Calc Chat. 35's at Calc View. And let's see. I think you can do 41. And then any of the odds 43 to 47. They're all at Calc Chat. 43's at Calc View. And try doing 49. 51. They're both at Calc Chat. 53 or 55, they're both at Calc Chat. 53's at Calc View. Hold off there. We'll pick up the rest of those later. All right, and folks, please try to get me tomorrow. We're having class 9 to 10:15. Not going to be here, okay. And but it'll be on YouTube.
Get off at 9, so I'll try to get over.
Okay. All right.
I got this science class with Nelson.
What's that?
This science class with Nelson on the Birmingham campus.
Okay, well, it'll be on YouTube, so you can follow it up later. Okay, I need those tests or papers or something in, so I don't have to give you an income failing at midterm.
Do
Okay.
you know when you'll have those graded by the test?
I have everything graded that's been in so far. I just don't have them posted yet.
Okay.
But if you want to see your score, you certainly can. Okay. Yes, sir.
Okay, so can I get my take-home test?
Okay, did you get the first one? Or the second? I doubt if you have those finished, do you?
No, sir.
Okay.
Finished it today. I'm going to a space summit.
What's that?
I'm doing finish today.
Okay. All right. Are you needing one or look at the score? Huh?
I need the second. What's the second?
I can't hear you.
I need the second test.
Second test, okay. All right, while you're here, Jake wanted to see his score. Oh, terrible, okay.
You mad?
do I not have? I don't know where my test is going. I may have to run you off one, because I know I had enough copies. I have the first page, but I'm missing a second page, so I have to copy you the second page.
Okay.
Okay, I'll be right with you.
Okay.
You need a second test too, or?
I need the second test.
I think
Test
I
two.
know. Second, test two. So both of you need test two. Wait, no, this is test one. So you need to, here's your page one, and you come with me and I'll get the second page. So I have to make a copy.
Okay.
And you both need test two, so hold on. Now, I'm pretty sure I've got
I ain't
that.
got it with me, so I'm gonna be right here.
Okay,
So I'll put it in there real quick.
okay. Here's test. There's one test two, and there are 9 graphing problems on there. So I'm going to give you
Another paper. 2 of them.
2 pieces of graph paper printed front and back. Do 2 or 3 on each side.
Okay.
Okay. Now, why am I missing one of those 2? Yeah. Check that and make sure that's not my original.
Is this your original?
No.
No.
This is bizarre. Because I know I made enough copies. Ah, here it is. Here's your test 2. What the deal was, I didn't have the, I remember now, the copying machine went bonkers. Okay, here's your graph paper. You need graph paper?
Yes, sir.
Try to do at least 2 per page. 1 page will need 3, because there's 9 to be copied, but that's front and back. Okay, so you still need the second page for test 1. I bet you it's going to show up somewhere in here, but rather than waste time on it, let's just go get it. And by the way, I've been recording all that.